conference, Nullcon Online 2021 edition would have not been successful without the support of our sponsors. So yeah, if you all are interested to see for any job openings in our sponsor companies, please do check out our career page on the Nullcon website. They have some really amazing openings, and you can work from home as well, so you don't have to travel. So yeah, the next talk is by Lilith. 2020 has taught us all how to work remotely and online, organize more collaborative mechanisms to work online digitally. So Microsoft Azure had a 3-month bug hunt challenge, and Lilith reported 16 vulnerabilities on these custom SOCs and patched Linux kernels, gaining privilege escalations and a lot more. So Lilith is part of the Cisco Talos team, and she focuses on IoT security. She's a trained boxer, which I think is super cool and amazing. So yeah, Lilith, I would request you to start your presentation.
All right, here we go. All right, one sec. Sharing the correct screen. Okay, here we go. Hi, everyone. So my name's Lilith. As previously introduced, I am from Cisco Talos. And today we're talking about the Azure Sphere custom SOC. I am a researcher from Cisco Talos. I'm on the Vuln dev team. We just hunt ODAs and products. We get a lot of freedom for what we look at. We've got people looking at like Mac OS, Windows kernel. I typically focus more on like Linux kernel and IoT stuff and networking. So the idea is we take our ODAs, then we take the signatures, we throw them in like Snort or AMP or like all of our antivirus and signature products. So that's the reason we exist. And so I have a GitHub. I don't know, that's basically it for me. I have to do an obligatory shout out because I didn't do this work alone. I have a teammate, Claudio Bazzato, who I always work with because he's a cool dude. So I always have the slide here because like, I don't know, I feel bad giving these talks without him or something. I don't fucking know. Anyways, so for the presentation, this little bastard. So this is the Azure Sphere, this little thingy thing here, the MT3600. But yeah, as mentioned before, Microsoft hosted like a 3-month vulnerability challenge. We were invited to participate. A lot of different companies participated. I don't know how many people actually worked on this thing, but there was like 70 people in the Slack chat room. So if that's any like indication. But yeah, it was essentially like a CTF on a production on like this little device thing, and it got patched every month, which was a pain in the ass. As mentioned, it is the MT3620, which is a custom Microsoft / MediaTek SOC. It's 4 cores. You got 3 Cortex M4s and a Cortex A7. All 32-bit ARM v7. It keeps its Linux kernel relatively up to date. So you're looking at like the 5.4 branch and above. I think they started at like 5.4, that like when we started. But anyways, so the Linux kernel runs on the A7, and then you got 2 Cortex M4s that can run like real-time RTOS custom applications. So the idea is like your developers will flash applications to this hardened IoT device. So you don't have to deal with like custom hardware, custom firmware, custom kernel or anything. Like Microsoft's trying to take care of all that for you. And then you flash your application, and then the device like makes sure it's all secure and like can do cloud stuff, you know? So continuing on. Because it's ARM, it has the ARM trusted environment, the T. That is, there's 2 main, like really secure parts of the device, which are security monitor, which could be found at /dev/security monitor, and then /dev/Pluton, which is like the secure processor for like handling keys, handling crypto, handling like hardware RNG, and so forth. So continuing on. But yeah, so the device has a lot of cloud functionality. the device actually has to authenticate to the cloud in order to gain access to the network services that Azure's that the Microsoft Azure cloud provides. So if your device has been compromised and like something's gone wrong with it, odds are it's probably not going to be able to successfully pass verification, because there's like a hash of every application done, and it's super secure and stuff. Anyways, I didn't really pay much attention to that because it wasn't in, I didn't really care. But yeah, anyways, so continuing on. So what we did, you can flash applications in two ways. If it's in a developer mode, you can flash it via USB and the little USB port thing in the back. Alternatively, you can also push your application via the cloud, but that's if it's in like production mode. So some more like cool novel things about the device is that all applications and firmware on the device consist of this, let me see if I can get a laser pointer going. Oh, can you see that? Hopefully. This ASXipFS. I just call it ASSIP because it's easier to pronounce. But all ASSIP partitions are non-writable. You just, the kernel driver does not have a write function, so it just can't fucking write. But it can execute, and so it's a special type of partition called a XIP partition, such that it doesn't actually load this flash memory into RAM when it executes. It executes it straight from the flash, which is why it's called execute in place. It's pretty neat. The other thing that is really neat about it is that the only writable memory on the device is in a particular partition /mount/config, which is a particular partition. It's just there. The cool thing is, though, you can't write to anywhere in memory that you can execute, and you can't execute anywhere on the device that you can write to. So if you're familiar with like, what is NXP, or sorry, what's the execute or write? That's the, I forget the official name, whatever. Like, you can't write shellcode to this device normally and then execute it. That is like considered a bug for this device. Whereas like normally, you know, on a Linux device, you've got like 30 different ways to execute shellcode. On this thing, you're not supposed to be able to do it. So another interesting thing about this thing is that when a developer flashes an application, it needs an app manifest.json, which is like a schema file for what it's allowed to actually do. And this may sound interesting, but like even for such trivial tasks as like connecting to one IP address, it has to be defined in your JSON file. Even if you want to have like 4 kilobytes of storage, that needs to be defined in the app manifest.json. So it's very granular and pretty locked down. So in this slide, we can see like this is an example of a app manifest.json. This component ID is just an identifier. These capability fields are like defining what exactly is this device allowed to do. So it only has 64 kilobytes of storage. It can only bind TCP ports 5555 and 4444, and it's only allowed to connect to one IP address. So these are enforced by a lot of permissions. So like, if you pwn this device, if you pwn an application running on this device, and then say you try to connect back to your you try to connect back to your CNC server, like unless it's defined in this schema file, or you find another vulnerability to bypass this, you're not going to be able to do that. So that's the idea of why all of this exists. So continuing on, this is like a high level overview for the managers, the not as technical folk. It's a nice graphic. I like it. We have our Cortex A7 here. Normal Linux is inside the A7. We have our device drivers. You have Pluton here, which you can talk to via this driver. You have /dev/security monitor, which lets you talk to the ARM trust zone. And then there's assorted other things. For the more complex version, for my homies out there, my nerds, we have an ASCII diagram too. if you want to, I don't know, look back at the slides if you actually care about this. I'm not going to go through it all. It's not that important. But what is important is that for the Azure Sphere Security Research Challenge, there were quite a few things in scope. The main things they wanted to know are if you could get on Pluton or the secure world. I didn't care about this. The most interesting thing, in my opinion, was that anything allowing unsigned code execution that isn't ROP was considered a vulnerability. So like I said before, if you can take shellcode, put it on the device, and then execute it, it's considered a vulnerability. And that's something that's novel, that has not been done before. And so it was a really interesting protection that we thought, and we bypassed it in quite a few ways. But yeah, another interesting thing to note, they didn't really care about any DOSes, which I found kind of funny. Even if your DOS like bricks the device, they didn't really care. But yeah, so these are all the vulnerabilities we discovered. I believe it was 16, if I can count that high. So we had, I obviously don't have time to cover all these. But so these are the cool vulnerabilities, because admittedly there are a few lame vulnerabilities, but hey, a bug is a bug, right? But because of time constraints, we're not going to cover that many. So these 4 down here, the ones in orange, were our escalation chain. So we're going to cover the privilege escalation chain, going from installing an app to having Azure Sphere Capabilities, which is the highest credentials you can have in the normal world. Sorry, the Linux normal world on the Cortex A7. I'm also going to cover maybe 1 or 2 of these, the unsigned code execution bugs, just to like give an idea of what it takes to actually execute shellcode on here that's not just ROP. All right, so yeah, skipping this, unsigned code execution. So this, like, I like it because it was novel. You know, it was something new. It's a new protection. You haven't seen it before. So they actually had quite a few protections in order to prevent you from loading shellcode and then running it. Like I mentioned before, only executable data that is on those asset partitions only data on the asset partitions are executable. You cannot execute data on something that is not on an asset partition or on asset flash. And so, like I said, those partitions are non-writable. It's not just that they're mounted not writable, it's that there's no write functionality in the kernel driver. The only writable data, the only place you can write is on the little fs partition /mount/config that is not executable. And then the little fs partition is mounted no exec. Continuing on, because I know some of you clever people are like, well, why don't I just load shellcode into memory and then like mmap executable code? But they didn't miss that. So what they do is they have custom Azure Sphere Linux security module functions to check certain kernel functions. So if you mmap a file, or if you mmap memory, right? Because normally if you have shellcode, you're just like, I'm just gonna mmap like a fucking writable and executable piece of memory. But Azure Sphere checks to make sure that your mmap request is not writable. If it is writable or executable, you are not trying to do both at the same time. So you cannot mmap something with WX. You just can't do it. It's prevented here. Likewise, if you're trying to be more clever and you're like, hey, I'm just going to fucking map something executable that's shared and then map it as writable and shared in another process and then write to it from this process and execute it in this process, you can't do that. You cannot map a shared page as executable. That's what this says here. Continuing on, because we're not done. We're getting in depth. So that was for mmap, but we also have mprotect, which is another syscall. Likewise here, if you try to mprotect a piece of memory as executable and writable, it just doesn't let you do it. If this one's fun, if a page in memory was writable, or is writable, and then you try to change it to only executable, you can't do it. if it was only executable and then you try to change it to writable, you can't do it. And likewise, if it's shared, you can't change it to executable. And last thing, I swear, this is the last one. If a page was ever writable, it cannot be executable. That's what this does here. It actually stores extra data in this may exec flag, which I didn't know about this before. So, I mean, hell, I didn't really know about much kernel stuff before this, but wait, it wasn't the last one. There's one more. I guess there's another one that just doesn't let you map something as writable if it was ever executable, or the other way around. There's a lot of protections, I guess, is to summarize it. So these are all the ways we found to bypass it. So we managed to bypass these protections in 5 different ways. Some of them are funny, some of them are actually cool. But so I'm not going to talk about all of these because, for instance, this top one here, the Azure Sphere Ptrace. What we did is we have a process, it forked, we ptraced the fork with our parent process, and then we could just write into executable memory because ptrace is special like that. I mean, it's kind of lame, but you can do it. This one was funny. Fun fact, every process has a file that lets you write to it that is essentially its memory space. And so if you just write to executable memory this way, you can execute shellcode. So you just have to be a little creative with these ones. But 3 of these are simple. 2 of these are not simple. We're going to cover maybe 1 or 2 of these depending on time. So for the first one, I might skip the second one depending on how I'm feeling. Read implies exec. This is a fun Linux fact that I did not know about. So when you execute a Linux process, it has a personality, quote unquote, that lets you change certain characteristics of that process. I mean, you can read the man page. It's probably a lot more descriptive than I am, but 2 of the characteristics that you can change that are really interesting, in my opinion. Well, we only care about this one, but I don't know. Anyways, read implies exec is a personality trait that you can set for a process that when you mmap a page as readable, it implies executable, which is great for our opinion, or for our purposes, because like generally the Azure Sphere protections for this sort of thing happen when you try to mprotect or mmap something as writable. But if read implies exec, we're never touching writable, right? So anyways, so carrying, it's important to note, I guess, that like, one second. I guess the breakthrough came through in that like in finding that like the VM data default flags stores read implies exec. It's a flag in your process. And so figuring out that like this particular define carried that information allowed us to find this piece of code in do brk, which is essentially do mmap in the kernel. So when you do brk, which changes the boundaries of your Linux process memory, so it like expands the heap or the stack. That's what it does. When you do brk, this VM data default flags is actually taken into account in the process, like the code flow. And so our read implies exec is actually carried in this flag down here, which is kind of useful. So if we map something as readable and writable, RW, because VM data default flags carries read implies exec, this thing's actually going to be mapped as RWX. There were a few extra steps though. It wasn't just this one little thing, this one simple syscall. We also have to make sure that the memory that we are mapping cannot be mapped with another page. So for example, if I have a heap chunk like this, and I have another heap chunk down here, if my request to expand memory is like this big, it could expand into the next memory space. But if I expand my heap chunk up here to be like, I don't know, 10,000 bytes, it's going to be shifted down here because there wasn't enough space up here. That's basically all we're doing. And so, oh man, I hope you guys can see me. I'm doing a lot of hand motions, and so I don't want that to be lost on y'all. But anyway, so assuming that our memory request cannot be merged with another mapping, a new allocation occurs here at kmem cache zalloc. I got a scratchy throat. And then finally, our flag shield that contains our read implies exec is thrown into the VM page protocols, which allows us to run this simple shellcode. It's really just that easy. So all you got to do is set a personality like so. You set read implies exec. You call brk0, which we use syscall because their Musel C libraries are shitty and didn't have brk0 defined. And then you can just literally call this shellcode. It's that easy. So that is what I mean, though, by unsigned code execution, is that loading, once again, just to reiterate, loading shellcode on the device and running it is a non-trivial task. You need a vulnerability in order to do it. And so it's another step in the process to just make this shit more complicated and harder for attackers. How am I doing on time? I think I'm going to skip this, actually. Well, we'll go through it really quick.
You have like almost 10 minutes, so you can 10-15 minutes. So yeah.
Oh, okay. Yeah, I'm skipping that. Sorry. A TLDR. Oh God, too far. There we go. So the escalation chain. Let's go through this really quick. So start to finish, we install an app and we end up having the best permissions in the A7 pretty much, or not the A7, but Linux userland rather. Ours consisted of 4 chains. Something worth noting, McAfee ATR, which is another team that participated, actually discovered they had a bug chain that overlapped with this and like 2 bugs, which was kind of cool. But theirs diverged and they ended up getting crappier credentials. We got the cooler credentials. So that's why I'm talking about it. But no, they did great work. They actually ended up finding another bug that was really cool, which let them install an arbitrary application. But anyways, continuing on. Right, so to start off, like I said, the ASSIP partitions, this is what they look like. You can see type ASXipFS. They're read executable. You cannot write to them. I already showed you this. Oh, this is like an applications like tree, right? So you have your app manifest, you have the binary folder, and then you have the application. This is like packaged up into an image package, which is ASXipFS, and then flashed to the device. So really quickly, what an ASXipFS partition looks like is you'll have a bunch of headers. These are what the headers look like. This is like a standard file system image. It's not that special. Then you have a bunch of inodes after the headers. The inodes consist of inode headers and then inode data. We can see an example of like what the inode headers are down here. Interesting to note actually is the UID and the GID of the file is actually contained here, but it's completely ignored by the system. So, because otherwise we would have just flashed an application that had root credentials so just right then. That would have been lame though. We can't do that. So something to note, when you, well, back in the day, I say back in the day, like last summer, whenever you accessed an ASXipFS inode, there's interesting things that can happen. So for regular files, there was one code flow, right? If you access a directory on this partition, then you get different operations that can happen, right? Because that's how a file system works. But interestingly, if it wasn't a directory and it wasn't a regular file and it wasn't a soft link too, then there was actually this init special inode function that happened. And the init special inode function was actually located in Linux itself. This wasn't Azure Sphere specific code. So if you'll notice here, if it's a char device, then it loads the char device operations. If it's a block device, it loads the block device operations and so forth. And so if you've ever like installed a block device onto a file system before, it's a pretty powerful thing you can do. So like I said before, we couldn't just change the UID and GID of the files on our partition, but what we could do is we could create a block device via the minor and major numbers of a given device, and essentially have a soft link to another device on the file system. So like /dev/mtd block 0 or something like that, because we essentially have a soft link that we can arbitrarily point to devices, and we have permissions to actually read these devices. And so we use this to actually access the little fs partition. By default, you only have one folder in that partition, but by using this ASXipFS bug, we could in fact access the MTD block device, the blocked device driver for MTD block 0. And if you'll notice here, this is what /dev/mtd block 1 looked like before our exploit. And this is what it looks like after. We have root up here, but we have sys and then UID 1007 down here. We are UID 1007, and such, because of that, we gain read and execute permissions on the block device. So not write, but read and execute. So it's something. It's not nothing. It's something. So now that we can actually read the MTD block, the little fs, which is like stores configuration files, we emulated it in QEMU using the block to MTD driver right here. It's a pretty easy thing to replicate after we dumped the entire partition. So we took their partition from the device and we mounted it in QEMU to figure out like what was on there, what files were on that partition, and so forth. The key file on the partition is the UID map. The UID map maps UIDs, obviously, to component IDs. This is like an identifier that is flashed by our application. So all these are hard-coded system apps with hard-coded IDs, but ours changes every time we flash something. Right. So continuing on, what do we do with read and execute permission for the block device? We dumped the partition and we can read the partition. That's good. That's information. But we need to be able to do something more. It wasn't enough. So if we started to look at the ioctls for MTD char devices, and this is in the Linux code, not Azure code. So this is a cool bug. It's a Linux bug, not an Azure bug. And so we looked at the ioctl code and we noticed that in order to call memorace, because it's a flash device, you need write permissions here, as you'll notice here. But until about 3 months ago, you didn't need write permissions to call memwrite via mtd char write ioctl. So you could actually do a memwrite ioctl on an MTD block device without write permissions. You only need to read permissions and execute permissions. So, I mean, that was a Linux vulnerability. And so just to show like the code flow and that there's no writable checks anywhere. Yeah, essentially, if you want the long explanation, Claudio gives a really good explanation of what we can do with just memwrite. I'm not going to cover it because it was difficult. I'm just going to say, and because I'm running short on time, a TLDR is we can write to any file on /mount/config via the block device ioctl because of little fs and because of our second vulnerability. And so, yeah, you can read that in your own time. I don't got fucking time for that. All right. So where are we right now? In /mount/config. Okay. So back to the UID map. Since this thing maps like component ID to a UID, let's mess with this file, right? And so something key, this file is only checked when an application is spawned, okay? That'll come up later. So it checks this file, looks to see what component ID is running, and then assigns it this UID. Okay. So some rules for the file. I'm just gonna say, you can't mess with it too much. You can't have duplicate component IDs, these things over here. All the component IDs, you can't have all nulls. All the UIDs have to be greater than 999. You can't just set yourself to root. That would be cheating. Any error in this parsing causes the file to be recreated. But there are two things that were not checked for. And this is actually where our bug chain and McAfee's bug chain split. So what McAfee did is there was a bug if you assigned a UID greater than 65535. What we did is we exploited the fact that it never checked to see if there was duplicate UIDs. So if there was like 1001 here, right? And so I'm going to come back to that slide and that one apparently. So yeah, what we ended up doing is we changed our UID for the application to that of Azure D, which is a daemon that runs on the device, which has a lot of permissions. And so moving back 3 slides, another key fact is that when an application is spawned, it also gains Azure Sphere capabilities, not just a UID, but these aren't Linux capabilities. They're more special than that. The Azure Sphere capabilities let you play around with Security Monitor and Pluton, the very that's like the holy grail of this device. So those are what we're aiming for, okay? So when you spawn an application, if your component ID matches this, one of these, there's like 5 hard-coded, we can see them all here. If it matches one of those, then you get the special Azure Sphere capabilities. Okay, skipping this. So we ran into a problem though, because even if we duplicate our UID, it's whenever a process is spawned, this file is checked. So we can't just change the UID. We have to change the UID and then have our application spawned. But we can't have our application spawned because that'll kill our exploit. So what we ended up doing is we had like 10 DOSes that we found in the thing. So you could just literally I don't know, respawn your application via a DOS and it would work fine. That's all you needed to do. But they don't count for bounties because who knows why. Anyways, so I guess our bug chain was actually like 5 bugs long, but yeah. So after we change the UID file, then we pop one of our DOSes to reboot the device. Then finally, our application spawns as a UID of like a different process, Azure D, which is a powerful process. But what does that actually give us? We don't yet have Azure Sphere capabilities though, because Azure Sphere capabilities depend on the component ID, not the UID. So in order to have the Azure Sphere capabilities, which is what we need to talk to the Holy Grail, we need to have the same like this thing, right? Unless we pop another bug. So bug number 5, I swear I'm almost done. Azure Sphere capabilities are stored in a different structure than normal Linux capabilities. Whereas normal Linux capabilities are stored in the cred struct, Azure Sphere capabilities are stored in this special little struct. So interestingly, since we have the same UID as this powerful process, Azure D, we can pass this check in Ptrace may access. Because we have this, as you'll notice here, we have the same UID and the same GID as our target process. We can now attach to it because of Ptrace, right? Normally, there's an interesting fact though. Under normal circumstances, there is a check to make sure that you cannot Ptrace a process with more Linux capabilities than yourself in order to avoid privilege escalation. But like I said, these are not Linux capabilities. These are actually special Azure Sphere capabilities. And as such, Linux doesn't even know they exist, and Azure Sphere doesn't check them. And so because of that fact, once we have the UID of Azure D, we can take Ptrace and just attach to Azure D. And we injected a reverse shell via Ptrace and then had it connect back to us such that we have these Azure Sphere capabilities. And so with bug number 5, we could actually finally talk to the devices that we wanted to talk to in the first place. So, which is the best credentials we can get in Linux normal land. So that's it. That's the talk. So I probably ran over time. I apologize.
Lilith, thank you so much for this amazing presentation. I'm curious to know what does Azure respond back to you when you reported so many vulnerabilities? Before that, did they know that you were a trained boxer?
Yeah, maybe they were afraid or something. Well, no, actually, so am I still screen sharing? I don't want to.
Yeah, you're still screen. Yeah.
Oh, do you still? Well, stop share. Okay, so I'm done screen sharing. But so the thing was we had to like report them in waves, right? Because you have to understand for the Azure Sphere Research Challenge, every month things got patched. And you also had to understand, because there were 70 other researchers, we were like, oh shit, we gotta, while we normally wouldn't have turned in these bugs, I'm like, I'm not gonna burn my bugs. What the no, I want to get higher escalation. But under certain circumstances, we did have to burn certain bug chains that normally we would be like, no, we want to keep going, just because we didn't want to lose out on like the credit, right? And so that we actually got really lucky because we submitted our bug chain the same month that McAfee did. And if we hadn't decided to play it safe on that 1 month, we would have had our entire bug chain burned and we wouldn't have gotten any recognition for it. So we played it safe. But as for their reaction, they were cool about it. Sometimes they just closed the bugs for no reason, like right away, because they didn't read the bugs or something. But aside from those little missteps, it was okay.
All right. I think it was an awesome talk and amazing research by the whole Cisco Talos team. Thank you so much, Lilith, for this amazing presentation.
Thanks for having me. All right.
Our pleasure.
Bye.